Okay, um, to start working with center of mass or center of gravity, I first wanted to introduce to the class what that kind of means. And so I took an example, said, here's a plank that has a mass of 10 kilograms, and we have a 70 kilogram person sitting on the very end here, and a 90 kilogram person sitting in a little ways, 1 meter, and said, where is the balance point? Where would we have to put the fulcrum so that this was balanced? So, um, so we're going to go to there's a three. I'm going to go three times through this problem finding that point. By first, I'm going to imagine this being on fixed here, that this is a turning point called, I'm going to call it a pivot point. So I'm thinking this whole system is pivoting around this point. Therefore, some of the masses here are going to try to make this thing turn clockwise, and some things are going to try to make it turn counterclockwise. And I'm going to make a little table of that. Clockwise and counterclockwise. So I'm just going to go through the masses. I got a 70 kilogram mass. It's sitting right on that point, so it's not causing it to twist either way. The plank, 10 kilograms, is pushing down on the weight of that. Will be trying to make this, the plank will be trying to spin clockwise. So I got 10 kilograms. And when we got something creating a twist, if it's close in, it doesn't force it around as much as it does out here. So the amount of twist, called torque, is dependent on how much the weight is in actuality, but weight would be just these multiplied by the acceleration due to gravity, 9.8. But everything is going to be times 9.8, so we can forget that for a little bit. But I'll call it torque, but it's not really torque unless I'm talking weight, a force. But it depends on how much the mass is, which controls weight, times how far out it is. Well, some of the plank's clear out here, some of it's right here. On average, is at the middle. So I'm going to say the lever arm for this weight, mass times 9.8 weight, is 2.5 meters. This mass is also trying to make it go clockwise, it's pushing down on it. That's 90 kilograms, and if I wanted to make it torque, I'd multiply by 9.8. But forget that. And it's out from the pivot point, it's out here 4 meters. Well, that seems like there's all that's there. But remember, we have to hold this system. We got to push up to hold it up. So somewhere here, someplace out here, some distance x, we got to push up enough to hold these three masses, or weights if I multiply them by 9. We got to hold all of those. So that's 70, and we got to hold the 10, and we got to hold the 90, and we got to push up someplace out here x. So to be in balance, the amount that's trying to push it counterclockwise has to equal the amount that's trying to push it clockwise. So 10 times 2.5 is 25. 90 times 4 is 360. Has to equal 70 plus 10 plus 90 is 170 times x. So if I take the 385 divided by 170, that should equal where this balance point is, the center of mass on this, since we're only dealing with masses. If I multiplied everything by 9.8, I'd be finding the center of gravity. So I got 385 divided by 170, and I get 2.265. 2.265 meters. Not quite halfway. Now, let's do this calculation again. This time, I'm going to move the pivot point to a different spot. I'm going to put it at the other end. And the reason I want to do this is to show you that it does not matter where you imagine the pivot point is, as long as you work everything from that place. So if I do that, this 70 kilogram is going to be trying to push this down in the counterclockwise way. So I got 70 kilograms. That is how far away? 5. I have the 10, which we're going to think of as being at the center. So we have, that's going to be pushing it counterclockwise. So we got 10 times 2.5, 10 kilograms times 2.5 meters. And we have this 90, which is 1 meter out. So we have 90 kilograms times 1 meter. And we have to push up someplace from this end. I'll call that, okay, I'll call this Y since that's a different one. And it's got to lift, it's got to hold, it's got to push hard enough to lift all of this, to hold all of that. 70 plus 10 plus 90 times Y. And so I get 350 plus 25 plus 90, which is 375, 415 divided by, and that's equal to 170 Y, and so I divide by 170, and 415 divided by 170, and I get 2.44. Did I add those up right? 350, 440, 465, 465. I didn't add them up right because the number didn't come out right. 465 divided by 170, and I get 2.735. 2.735. Well, 2.735 from the meters from this end is exactly 2.265 meters from this end. So we ended up with the pivot point being in the same place. And I'm going to do it one more time. Let's say we put the pivot point somewhere in the middle here. How about we think it should be right at the middle? So we're thinking of it at being 2.5 from this end. If I do that, let's see, I'm going to be able to show you as I do it. So I'll do it over here. That way, the 70 is 2.5 from here and causing it to go counterclockwise. Times 2.5. The 10, the plank, if I put this right in the center, the 10 will be balanced on it, so the 10's not going to make it twist either way. The 90 is going to cause it to twist clockwise, and that'll be If that's 2.5, this is 1.5. And then we got to lift it. Well, I just guessed that this might be the lift point, but the lift point might be someplace else. And we know already that it's over here, but I'm going to play dumb and pretend like I thought it was over here. And so I'm going to say I have to push here, which is going to push it counterclockwise. I'm going to push enough to hold all of this, so that's 70 plus 10 plus 90 times x. Now, you'll see that it's going to tell me that I put it in the wrong side by the signs on this. So I have 90 times 1.5, which is 135, equals 70 times 2.5, 140 plus 35, 175. Let's just check that. 2.5 times 70. 2.5 times 70 is 175, yes. Plus, this is 170 times x. So if I subtract 135, I get negative 40 equals 170x. Divide by 170. And x is going to be a negative number, which means I put it on the wrong side. It's going to tell me to put it over here a little bit. So negative 40 divided by 170 says I should have put it over there 0.235 meters. 0.235 this way. Well, 0.235 from 2.5, where I thought it was, we'll put it right there again. 0.235 meters. So, point being, no matter where you think the pivot is or where you imagine doing the system at, you'll get the center of mass by taking all the torques, the masses times lever arms, divided by the total mass of the system. So the mass of all there, and you'll get the center of mass or center of gravity if you use weights here. So the summary, and I didn't do a good job of this in the class. If you take the total torque, which is masses times lever arms all added up, or weights times lever arms added up, divided by the total weight, the total mass, or total weight, and you will find the center of, if it's mass, you'll find the center of mass. If you use weight, you're going to find the center of gravity. And that's what we want to talk about in this next section. Center of mass or center of gravity. Okay? That's the balance point. And we're going to do this on the baseball bat to find its center of gravity.